So I've referenced the sensible heat equation, Q equals 1.1 CFM delta T, many times because it is a staple of HVAC design. But I always refer to it as the simplified sensible heat equation because it's not perfect. So I'm going to go over some of the other versions of the equation and give you a hybrid that gives you a lot more accuracy without a lot of extra work. So this is the sensible heat equation, simplified. You can use this to determine your sensible load based on a CFM and dry bulb delta T. You can also rearrange it to determine a CFM if you're given a sensible load and you know the delta T. Let's cross this out. This is the full sensible heat equation. This is not based on the 1.1 coefficient, which has a lot of assumptions built into it, mainly the mass of your air, the elevation. This actually takes your mass flow rate and the specific heat of your air to give you an actual. However, this equation requires you to find the mass flow rate of your air, which means you need to determine the specific volume. You probably need to use a psych chart to determine that. You need to know your elevation to get that, and it's a little more cumbersome to calculate. So let's cross this out, and I'm going to show you a really great hybrid. This is somewhat of a hybrid for the sensible heat equation. You still have familiar terms, your load, CFM, and delta T, but instead of making this big assumption with a 1.1 or a 1.08 coefficient, we're actually going to calculate the coefficient. This is the air sensible transfer factor, and this equation right here is how it is calculated. And it looks a little messy, but you'll see the only variable here is your elevation. So we can use this equation to actually determine the right air sensible transfer factor for our project at our location and our elevation, and we can keep all the other variables the same. So to break this down, we've got our 1.1, that's familiar, and then everything to the right uses elevation to adjust the 1.1 to more accurately reflect the state of air at your elevation. To demonstrate the importance of this, let's do a demonstration where we're calculating CFM for a building with the same requirements but in different locations. So we're going to compare Los Angeles to Denver. The requirements are we have 500,000 BTUs, space sensible load, and the delta T between your supply air and your space set point is 17 degrees. Now in Los Angeles, the elevation is about 0 feet. There are some places that are sea level, some places that are a little higher, but we'll assume 0 feet. And then in Denver, the elevation is about 5,000 feet. From here, we're going to calculate that air sensible transfer factor for both of these locations. To help with that, I've created a quick little calculator that uses that equation I just shared. So here I can enter the elevation and it will return the air sensible transfer factor. And if you want this, this is what that formula looks like in Excel. So at 0 feet, we're at 1.1. I'll write that down for LA. And at 5,000 feet, we are at 0.92. So let's get that down for Denver. And while we're here, if you're wondering where 1.08 comes from, let's try 500 feet. Hey, that's the assumption we're making if you use 1.08, about 500 feet in elevation. Okay, so now that we've got this down, we have all of our variables, we're going to rearrange our sensible heat equation to solve for our CFM. So for Los Angeles, let's crunch these numbers. Our CFM, given a sensible airflow factor of 1.1, comes out to 26,738. For Denver, with a CS of 0.92, this comes out to 31,970 CFM. So due to the higher elevation in Denver and the lower density of the air, you're actually going to need to provide 20% more CFM for the same project, same requirements in Denver than you would need to in Los Angeles. So if you're working on projects in the mountains, hills, cities with higher elevations, highly recommend that you use the hybrid formula or another calculator to determine the required CFM. Because if you sit on a 1.1 or a 1.08 coefficient, then you might be shorting yourself on the actual amount of airflow required to move heat. As always, if you like these videos and they're helpful to you, please share them with a colleague, another HVAC designer, or just let me know. It helps out a lot.